and welcome to another set of ICP video notes. Today we'll be learning about forces. So before we get into it, go ahead and copy down these vocabulary words. Alright, so first off, what is a force? A force is a push or a pull on an object. It's important to look at how hard an object is being pushed or pulled and in what direction it's being pushed or pulled. This makes force a vector quantity, and we represent it with vectors that point in the direction of the force and are relative in size based on their magnitudes. When talking about motion, we tend to use the net force to describe the motion. The net force is the sum or addition of all of the force vectors. So for example, if I have a table with a book on it, and I am pushing on that book with 20 newtons of force, and my evil twin is also pushing on the book with 20 newtons of force, but in the opposite direction, we have two vectors pointing opposite ways, 20 newtons each. Since they're opposite ways, they cancel each other out. That gives us a net force of 0 newtons, so the book's not going to move. Now, say my evil twin skipped leg day, and he can only push with 5 newtons of force. I'm pushing with 20 that way, he's pushing with 5 this way. That gives us a net force of 15 newtons that way. Now let's say my evil twin turned to the good side and we both were on this side of the table and we're both pushing with 20 newtons of force on the book. Then our force vectors will add together, giving us a net force of 40 newtons that way, and the book's going to go flying off the table. When the vectors are in the same direction, we add their magnitudes, and when they're pointing in opposite ways, we subtract them. Then the direction of our net force would be whatever direction the larger force vector was. In order to examine net force a little more closely, we should probably start drawing some force diagrams. A force diagram shows you the object and all of the forces that are acting on the object. So we start by drawing the object. If an object has anything attached to it, like a string or it's sitting on a table, then we draw those things too. When we draw our force vectors, we always draw them from the middle of the object and go out. So in this class, a lot of our examples will involve an object sitting on a table, a flat table more specifically. There are always at least two forces acting on that object, gravity and the normal force. Gravity pulls things down towards Earth and is relative to the mass of the object. The bigger the object, the larger the gravitational force. The gravitational force vector always points down. Now the normal force always points perpendicular to whatever surface the object is sitting on. So if we have a flat table, the normal force vector is going to point directly up. If the table's tilted, it would point in whatever perpendicular direction is tilted. So when we have a flat table and the normal force is pointing up, that force opposes the force of gravity. The vector of the normal force on a flat surface will be the same size as the gravity, but just in the opposite direction. So there's a couple other forces that we'll deal with in this class. These are the applied force and the force of friction. The applied force is imposed on the object by another object. This is the force you most often think about when you think about pushing on an object. The force of friction always goes in the opposite direction of the applied force. Friction tends to increase with more applied force, but there's a limit to the friction based on how rough the surface and the object are. So if I take the book that's on this table, and I'm just standing over here looking at the book, you notice we have two vectors. We have the gravity going down, normal force going up. If I push on the book a little bit, we now have 4 force vectors. We still have gravity and normal force, but I'm applying a force, and since I'm applying a force, there's now a friction opposing my applied force. I'm not pushing on the book hard enough to overcome that limit to the friction, so we have a net force of 0, and the book's not going to move. Now if I push the book a little bit harder with just enough force to overcome that friction, the book starts to move. That's because my applied force was larger than the force of friction. Since the net force was in the direction of my applied force, the book was moved in that direction too. Now one question you might be asking is friction a force or not? Well, yes, it's considered a reactive force because it only occurs when there's an applied force present. If there's nothing pushing on the object, friction doesn't push on the object either. There are 3 types of friction, and you've already seen 2 of them. When there's friction present, but the object's not moving, we call that static friction. When there's friction and the object is sliding across a surface, we call that sliding friction. And then if we had like a round object, like a tennis ball, and we pushed on it, it would probably roll on the table before it slid, so we call that rolling friction. That's why if you push a ball down a table, it eventually slows down. Now, of all the forces we've talked about today, they can be categorized as one of 2 types of forces. We have contact forces and field forces. Contact forces are those forces that involve one object physically touching another in order to push or pull on it. Contact forces would include friction, normal force, and in most cases, the applied force. Field forces are those forces that act on an object without actually touching it. These would include forces like gravity or the force that pushes and pulls on magnets, which could be the applied force on an object too.